Professor Poddar, you can
Sure,
start.
sure. Okay. So welcome everybody to today's talk in this year-long series of virtual seminars organized by the Bhaskaracharya Pratishthan at Pune on the topic of geometry and arithmetic of Calabi-Yau threefolds. So today's talk will be delivered by Professor Charles Doran of the University of Alberta, Canada. He's also an associate member of the Center for Mathematical Sciences and Applications at Harvard University. It's a great pleasure for me to introduce Professor Doran. So over to you, Professor Doran.
Okay, thank you so much. Well, it's a great pleasure to be back after my first talk a couple of days ago. That talk I had handwritten out, and it was a slightly different style. Today, both in the interest of making it somewhat self-contained for people who want to watch just one lecture, not two lectures, and also because I think I can speed through the portions that are well known to the expected audience here. What I've done is I've created an amalgam of two talks. The first is a colloquium I've given many times in the past several years, most recently at Tulane back in April, so hence these slides, with the same title as this talk. And then when I get to the part in the talk where I'm talking about new results, I'll switch over to what I did yesterday in the Hosono conference, the birthday conference for Shinobu Hosono in Tokyo. So then I think people will get a bit of everything. They'll get a bit of a mix of the overview of this topic as explained in the abstract, and then also the details of at least one application. Okay, great. So the topic is mirroring towers, fibration and degeneration in Calabi-Yau geometry. And the rough outline after an introduction is going to be, I'll talk about nested Calabi-Yau manifolds. This is going to be closely related, but not quite the same thing as what I was talking about in some parts of the lecture from Tuesday. Then how mirror symmetry fits into this notion of towers of iterated fibrations. I'll mention the evidence in favor, and then I'm going to switch over, as I said, to one particularly new and interesting feature of the whole story. Okay, so the paradigm I want you to have in mind is Matrushka dolls. Okay, that we have these dolls of different sizes, and they all look more or less the same, although the level of detail gets rather low when you get towards the small one. And Matrushka dolls have the wonderful property that they nest. They sit one to the next, to the next, to the next. And I want us to think of these as being different dimensional Calabi-Yau manifolds, as we'll soon see. So it's a paradigm. It's been used for many things. If you happen to be an IT person, you can buy a set like this, and it reminds you of the tower of different orders of magnitude of data that you have to deal with in the IT world. But we're going to apply this paradigm to Calabi-Yau manifolds. Okay. Now, I know I don't need to tell you what is a Calabi-Yau manifold, but let's just go through it quickly in case anyone, perhaps a graduate student or even an interested undergraduate, is going to watch this video later. They're complex manifolds. So complex manifold just means that local patches on your manifold can be thought of as coming from a patch on a complex Euclidean space. In this case, we see a copy of the complex plane with period domains being strips, being identified by rolling it up into a cylinder. And over here, we see another copy of the complex plane, this time with a sort of an angled checkerboard pattern, also being rolled up in two directions. And that gives you the topological shape of a torus, but with its complex structure inherited from the complex plane. I should mention both of these objects down below are Calabi-Yau manifolds. They're just particularly simple ones. Okay, so it's a complex manifold. It carries something called a Ricci-flat Kähler-Einstein metric. I know that you've had at least one talk in this series that introduced these notions and talked about it and talked about the Calabi-Yau conjecture. I would say in the last 30 years, what's made them the hot topic that they are, in addition to just their centrality mathematically, is that they're needed for string theory. Okay, and of course, when people in the physics department come knocking on your door, as they did to Yau many years ago, and ask about how many Calabi-Yau manifolds there are, and you start making guesses and looking for constructions, it really drives the field rather quickly. Okay, so some examples. Well, we already saw we could quotient the complex plane by a lattice. That was the picture on the right in the previous page. So this is T2, the 2 torus with its complex structure induced by that quotienting. If you mark a point on it, it's an elliptic curve. So think of this as dimension 1 version of Calabi-Yau's or elliptic curves. Yes, they have non-trivial pi1, non-trivial fundamental group, and often in the definition of Calabi-Yau manifolds, as I'm sure you've heard before, we impose a simply connectedness condition, and we typically do that in higher dimensions to distinguish the Calabi-Yau manifolds that we talk about in higher dimensions from abelian varieties in higher dimensions. But in dimension 1, elliptic curves are all you've got, if you're compact. Dimension 2, well, here's an example. You could take the product of 2 elliptic curves and quotient by the involution, which is plus or minus the identity involution. That's going to have 2 to the 4 equals 16 fixed points. You can then resolve it, and depending upon which category you like to live in, whether you're an algebraic geometer or whether you're a differential geometer, you might resolve it in different ways. But no matter what, you're going to do this resolution, and you're going to get something called a K3 surface, either metrically or algebraically. Not all K3 surfaces arise this way. By contrast, all elliptic curves arise in the way described up above. If you want a construction that works in arbitrary dimension, in dimension n, you can always consider smooth hypersurfaces of degree n plus 2 in CP n plus 1. Okay, so this is a perfectly reasonable construction. Once you look at it for all n, you can ask yourself, what does it mean in different dimensions? So, you know, for n equal 1, this is saying that it's hypersurfaces of degree 3 in CP2. Great. So that's cubic curves. That's elliptic curves realized as cubic curves in the plane. This tells you that another class would be quartic surfaces in CP3, or the famous quintic threefolds in CP4. And then a question that I often ask a live audience, especially when there are students in the live audience at this point, is, well, what does that mean for n equals 0? And then they think about it. And, okay, well, the answer is it's a smooth hypersurface, whatever that means, of degree 2 in CP1. So it's either a pair of points, or if it's singular, it'll be a double point. Okay, so that's what Calabi-Yau manifolds are in a nutshell. Now, much of the geometry of complex manifolds can be encoded in properties of complex line bundles, and specifically the complex line bundle that we care about the most in this context is the so-called canonical line bundle. You just take the non-vanishing section given by dz1 wedged through dzn on your complex manifold dimension n, with transition function given by nothing but the Jacobian matrix that we teach our students in advanced calculus. And oops, there we go. Sorry, I had another alarm. So a manifold is then Calabi-Yau if it's canonical. Did I skip a page? I think I did. Oh, no, I did. I defined it correctly. Yeah, the canonical line bundle. So a manifold is Calabi-Yau if its canonical line bundle, which a priori isn't trivial, is actually isomorphically trivial bundle. Okay, so that's the triviality of the canonical bundle is how it's frequently expressed. Now, a line bundle is trivial if and only if it has a nowhere vanishing section. So that means that Calabi-Yau manifolds come naturally equipped with a nowhere vanishing holomorphic n form that's unique up to scaling. So unique up to complex scaling by a non-zero number. Okay. Now let's go back to dimension 1. So elliptic curves admit a number of normal forms. There's the Legendre pencil, so it's y squared equals x times x minus 1 times x minus lambda. The Weierstrass equation, y squared equals 4x cubed minus g2 x minus g3. The Hesse pencil, that's the sum of xi cubed plus mu times the product x1, x2, x3. So these are all normal forms. And what's nice about them is that any elliptic curve can be realized possibly many times using such a normal form. But the choice of normal form affects properties of the families of elliptic curves that you're allowed to consider. So just because every elliptic curve shows up doesn't mean that all the families are going to be naturally associated as such a pencil, such a normal form. So you get modular curves naturally constructed to these as arithmetic quotients of the upper half plane. For Legendre, like I mentioned, y squared equals x times x minus 1 times x minus lambda, it's the full modular group of level 2. Okay, so the gamma of 2. And the holomorphic 1 form I mentioned, the omega 1, 0, is just dx over y. Okay. The Hodge diamond for an elliptic curve is particularly simple. You just have all ones. And over the modular curve, so if you like over this family, this base of this family, for each point in the base, you get an elliptic curve, and you can compute period integrals. You integrate the dx over y over a basis of cycles, like an A cycle and a B cycle, you get numbers. And those numbers moving over the base give you functions, and those are your period functions. And the period functions are annihilated by an ordinary differential equation of Fuchsian type, which in the case of an elliptic curve family is a second order linear equation. So that's the Picard-Fuchs ODE. What about going up in dimension 2 to K3 surfaces? Well, okay, for elliptic curves, we saw that being a branch double cover, so like the Legendre family, and being a projective cubic, like a cubic curve in P2, are essentially equivalent. You know, you get all elliptic curves realized in those ways, and you can actually have nice formulas translating from one normal form to another. For K3 surfaces, these have completely different generalizations. Okay, there are distinct geometric families of K3s. The double cover construction generalizes to, instead of double covers of P1 branched at 4 points, it's double covers of P2 branched over a smooth sextic curve. Now I say smooth sextic, but of course you could make that sextic singular at the expense of having to introduce singularities in the total space of the double cover that then have to be resolved. But in any case, the double cover construction generalizes this way. This gives rise to something called a degree 2 polarization. Think of it, if you like, as the fibers of the map to P2 are generically degree 2 points, if you want to think of it that way. But anyway, it's a degree 2 polarization on the K3, so it's a particular type of geometric K3s. You could consider quartic hypersurfaces in CP3. Fine, that fit into the original construction I mentioned on one of the previous pages. But if you do that, you get a degree 4 polarization. Okay, so these are not the same families. Now they'll intersect in an 18-dimensional family of K3s, but each of these turns out to be a 19-dimensional family independently of projective algebraic K3 surfaces. So not everyone can be in every family. You could consider complete intersections of by degree 2, 3 in P4, and you get a degree 6 polarization. And again, it's another one of these 19-dimensional families of K3s. And eventually, you want to generalize this notion to, if you like, arbitrary degree 2n. Okay, and that works, but you're not going to be able to do it anymore after a while as complete intersections in projective space. So the act of constructing these degree 2 depolarized K3 moduli spaces and the K3s themselves, it's almost easier to construct the moduli spaces than it is to construct the K3s themselves. That's sort of one way to look at it. Nevertheless, we have strong theorems, surjectivity of the period mapping, global Torelli theorem, that tell us that the K3 surfaces are completely characterized by this kind of period data. The Hodge diamond for a K3 looks like this. You can sort of see the ones we had before for the elliptic curve have moved off to the corners there. We have zeros here, 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 and here. And everything interesting happens in the middle, in that H11 part. As I mentioned, we have these different notions of polarization. And I also mentioned that if you have 2 polarization and a 4 polarization, say, you could have both, 2 different kinds of polarizations on the K3 surface. And what that means is that you're able to get an enhancement to your polarization from being polarized by, if you like, a single class to multiple classes generating a lattice. So when the rank 1 polarizing lattice generated by a single class is replaced by a choice of a primitive lattice of signature 1, r minus 1, you get moduli spaces of so-called lattice polarized K3 surfaces. Okay, and when you do that, the transcendental part of the Hodge structure, that is the part that matters, gets a 20 minus r. So if the Picard rank of the K3 is 20, generically say in your family, then the transcendental rank will pop up here and give you a 20 minus r. And of course, the middle dimensional cohomology you're seeing is 22 minus R, but it's 1, 20 minus R1 in terms of the weight 2 Hodge structure. Okay, what happens in dimension 3 and higher? Well, I'll start with the bad news. So in dimension 3 and higher, there's no known classification of projective algebraic Calabi-Yau varieties. Okay, and we certainly don't have a uniform construction of these. There's no known bound even on the Hodge numbers in that Hodge diamond for Calabi-Yau threefolds even. In particular, we know that Hn minus 1 for a Calabi-Yau manifold is going to be the number of complex structure moduli. So what this means is we have no known bound of the number of complex structure moduli, not even for Calabi-Yau threefolds. The good news, however, is there does exist a coarse moduli space for polarized Calabi-Yau manifolds with a fixed Hilbert polynomial, and that was established by Eckhard Liebeck. But the punchline of this is that most statements about the geometry of Calabi-Yau manifolds heavily depend upon the construction. Okay, I mentioned this at the Hosono conference that one of my motivations was I absolutely loved when I was in grad school that there were results like the unobstructedness of moduli of Calabi-Yau, sort of infinitesimal deformations or genuine deformations of complex structure that were universal. It was applied to any Calabi-Yau manifold, and even be extended to Calabi-Yau manifolds with a certain mild singularity type. Unfortunately, theorems like that are hard to come by. Most of what you prove about Calabi-Yau manifolds is going to be construction dependent. Okay, so to motivate our preferred construction of Calabi-Yau manifolds, let's look more closely at the case of dimension 1, the elliptic curve case. So again, we're integrating the holomorphic 1 form dx over y, the omega 1, 0 over certain cycles. When you do those integrals, you get elliptic integrals. And it's the elliptic integrals, which came out of problems in physics involving elliptical orbits and things like that. That's where the name ellipse comes from in the context, or elliptic comes from in the context of elliptic curves. Classically, the first of these elliptic integrals that was studied was Jacobi's sinus amplitudinous, and it's a doubly periodic function on C whose periods are given by complete elliptic integrals of the first kind. You can see how we've enhanced the sort of complex structure picture that I showed earlier for the 2 torus by now a further map from the 2 torus with its complex structure to CP1. Okay, and what's happening here is the sinus amplitudinous is a function of C, but it factors through the quotienting by the lattice, in this case, the lattice L, as it's called. And the map that it induces from the elliptic curve to P1 is a ramified 2-to-1 cover. Okay. If you want to view this as going backwards, you can start with this P1. And of course, this is all closely related to the triangle group section of this trimester. But you can start with this P1, and you can consider a multi-valued integral, this classical elliptic integral. And you can see the branching here would be at y equal, I guess, plus or minus 1, and y equals, what is it, plus or minus 1 over k, something like that. Okay, and we'll see more specifically how that works in the next page. So there it is. Here is your CP1. Here is your elliptic curve, your T2 with its double cover structure. Here's the 4 points where the ramification of this map occurs, and here's the 4 points that they branch over. Okay. Now, for reference, I put infinity down there just to emphasize that the fiber over infinity here is not one of these 4 points. The fiber over infinity is a pair of points on the elliptic curve. So, and what is that? That's specifying the pole behavior of your sinus amplitudinous. So specifying a pair of points in the fundamental domain for the elliptic curve at which the doubly periodic function has simple poles completely determines the sinus amplitudinous function among doubly periodic functions, and hence the double cover. Now, the elliptic curve is a Calabi-Yau one-fold. I already told you earlier that a pair of points or a double point is a Calabi-Yau zero-fold now inside it. So what you get is that choosing a Calabi-Yau zero-fold inside a Calabi-Yau one-fold gives you the structure of a codimension 1 fibration of the Calabi-Yau one-fold over CP1. Okay? And this is a completely general phenomenon in all dimensions. So as a corollary of the adjunction formula in algebraic geometry, you get the following proposition. This is something that I proved in a paper with Harder and Thompson just because we couldn't find a reference in the literature for it. So we just did it ourselves. But if S in X is a smooth Calabi-Yau n-1 fold in n-dimensional Calabi-Yau manifold, then the linear system of S is base point free, and it determines a map from X, the Calabi-Yau n-fold, to CP1 with the specific S you're talking about, the one you pick, as a fiber. Okay, so this is the generalization of what we said about the sinus-incremental tubulars. Okay, and sometimes you can even iterate this procedure. For example, the construction I mentioned on Tuesday with Momendier produces such things. So if you iterate it, you're saying you have 2 points sitting on an elliptic curve, sitting on, say, a K3 surface, sitting on a Calabi-Yau 3, all the way up to sitting inside your Calabi-Yau n-fold. And this matches the basic design paradigm of the Matrushka dolls. You're nesting the Calabi-Yaus. Okay. You're also getting fibrations from this nesting at every step. Okay, now remember that elliptic integrals describe periods of a Calabi-Yau one-fold. And what Momendier and I showed, as I mentioned last time, was that you can iteratively pass from these to generalized periods on the higher dimensional Calabi-Yau manifolds in such a nested chain using, and this is again tying it to the thrice punctured sphere picture that I mentioned last time, the Euler integral transform for hypergeometric functions, or equivalently the Hadamard product on the level of power series, suitably described, or the middle convolution on the level of the Picard-Fuchs differential equations. Okay, so all three of these give sort of an equivalent description of this going on. Now, I mentioned in the title of today's talk, mirroring towers. So now that we've got the tower, let's mirror it. I should say a few words about mirror symmetry in general. I mentioned some last time, I'll say some more today. So given one Calabi-Yau manifold, mirror symmetry, which came out of physics, asserts the existence of another Calabi-Yau manifold. The mirror of X would be Y, of the same dimension, whose features mirror those of X, but in unexpected ways. Okay, so the physicists think of these as dual compactification spaces, compactification spaces for string theories, but for dual string theories. So specifically, it's type 2A and type 2B is the way they do it. And one of them, you're focusing on the symplectic structure, the other, the complex structure. But you have both structures on both sides, and their roles are supposed to switch. So what I want you to take away from what I've said so far is I emphasize that every Calabi-Yau, in order to study Calabi-Yaus, you basically have to pick a method of construction. And mirror symmetry would then assert not only that to one Calabi-Yau you get another Calabi-Yau, but to every method of constructing a Calabi-Yau, there must be a mirror method of constructing its mirror. Okay, so a mirror construction of the mirror partner. So if we take smooth quintics, we know that we have a middle dimensional cohomology with 101 complex structure dimensions, deformation dimensions. Its mirror, the mirror quintic family, should have the property that you have 101 in H11. Okay, and there's several equivalent constructions of the quintic mirror, Calabi-Yau threefolds. The first one goes back to Green and Plesser. And the idea there is to take a highly symmetric family of quintics, quotient by a symmetry group, and resolve. Later on, Victor Baturev recast it as something involving combinatorial duality of lattice polytopes for Calabi-Yau hypersurfaces and toric varieties. But the large value of that, the second Betty number for the quintic mirror, that 101 we saw in H11, tells you there's a lot of room for divisors. And because there's a lot of room for divisors, maybe we can find a K3 surface inside it. Okay, so in fact, as I mentioned last time, the quintic mirror Calabi-Yau threefolds, quintic mirror, not quintic, do admit fibrations by high-rank lattice polarized K3 surfaces, and not just in one way, in many ways. By contrast, if you're talking about a generic quintic Calabi-Yau threefold, there's no room for it to contain a K3. There's only a 1 in H11, and that's taken up by the hyperplane section. The hyperplane section is not a K3. It's a quintic surface, right? So we cannot expect in general that mirrors of fibrations will be fibrations. Because we said that the fibrations in codimension 1 are going to come from this Calabi-Yau in codimension 1 that has to be one of the divisors. And we said that the mirror quintic has lots, but the quintic does none. Okay. Nevertheless, the mirror of nested Calabi-Yau manifolds has to involve the mirror of the hypersurface in some way, but how? Okay, so we know we got the fibration by marking the extra data of the codimension 1 Calabi-Yau and inducing the fibration. Where does that guy go? Where does the K3 surface on the quintic mirror go when you pass to the mirror? Okay, where's that data encoded? So
there is some disturbance, perhaps.
Yeah, I can't hear him, so probably.
He got disconnected on
can you hear me now?
Yeah,
Can you hear me now?
Yeah.
Okay. Do you still have the screen?
Yeah, I have a screen. We have a screen.
Okay, great. Okay, that was just the other machine that kicked me off. I'm doing this with 2 machines as a backup. Okay. Well, so I didn't say much more during the pause. Let's all pick it up. So a conjecture of mine with my former grad student, Andrew Harder, and former postdoc, Alan Thompson, which goes under the name DHT mirror symmetry these days, starts with this basic assertion that mirror to a fibration is the Calabi-Yau codimension 1 submanifold SA in XA. Okay, so that, as we know, defines a fibration. So a mirror is such a fibration, then is a degeneration. And the degeneration is a degeneration of the mirror Calabi-Yau manifold. I call this one XA, let's call this one XB, into a union of a pair of components. And each of these components has the property that it intersects the other, right? They intersect each other in another Calabi-Yau of 1 dimension lower. And the assertion is that the Calabi-Yau hypersurface is SA, which gives the fibration structure on XA, and this SB, which is the intersection of these 2 components, are also mirror to each other. Okay, that's the basic assertion there. Okay, so now our Matrushka doll analogy is complete, even down to splitting into halves. Okay, because the dolls separate. So what about the components Y1 and Y2? What do they look like? Well, these are what are known as quasi-Fono manifolds. Okay, they're geometrically simpler than Calabi-Yau manifolds. They're a natural generalization of projective space. You can think of, in the threefold case, them as threefolds blown up along certain curves. And they have the property that they, in their anti-canonical linear system, have Calabi-Yau manifolds. Now, mirror symmetry is not limited to Calabi-Yau mirror symmetry. There are other variants of mirror symmetry that have been studied, motivated by homological mirror symmetry, conjecture of Kontsevich. He and others in physics proposed a generalization of mirror symmetry that applies directly to Fano and by extension to Quasi-Fono manifolds. And the assertion there is that the mirror to a Fano manifold is not another Fano manifold. Calabi-Yau goes to Calabi-Yau, but the mirror of a Fano is what's known as a Landau-Ginsburg model. Okay, so a Landau-Ginsburg model, mirror to say each of the Y1 and Y2 that I mentioned above, consists of a Kähler manifold, lambda, with H1 equals 0, together with a proper map, not down to P1, but down to A1, but whose compact fibers are deformation equivalent to the SA we were talking about before. In other words, it's a fibration, but a fibration only over A1. But you have 2 of them. So the other part of our mirror conjecture is that the fibration on the Calabi-Yau manifold XA that's induced by SA, you can get by gluing the Landau-Ginsburg fibrations mirrored to the 2 components, Y1 and Y2. Okay? So you have your mirror Calabi-Yau XB, it splits into Y1 union Y2 intersecting on an SB. The fibers of the Landau-Ginsburg models are deformation equivalent to SA, each fiber over A1, now glue. Okay. Now, of course, this is a very facile way of saying it, and when we first formulated this, we had to do it on the level of topology in different settings. We have to be careful what category we're working in, but it seems to be a very robust prediction. So through the dual structures of fibration and degeneration, okay, we've unified the Calabi-Yau mirror symmetry story and the Fano LG mirror correspondence. Okay, great. All right, so there's been an enormous amount of evidence in favor of the mirror conjecture over the past several years. And I'm going to mention some of it, and then I'm going to switch over to as I said, the other slides that focus on one particular bit of evidence and an application, a theorem that doesn't depend on anything in mirror symmetry. But let's start. So first of all, there's precise compatibility between the classification and construction of MN polarized lattice lattice polarized K3 surface fiber Calabi-Yau threefolds that I did with Harder, Novoselicev, and Thompson. And the 40-year-old classification of Skovsky on classification and construction of smooth Fano threefolds of Picard rank 1. Okay, and that connection comes from the fact that, oh, well, you take a Calabi-Yau of Picard rank 1, Calabi-Yau threefold, and you imagine a degeneration to a union of two quasi-Fanos, quasi-Fano threefolds of rank 1. They're going to intersect on a 2n or whatever 2D polarized K3 surface. The mirror is going to be your MN or MD polarized K3, and the mirror to that K3, and that will be the fiber on the Lambda Ginsburg models that then get glued, and you check that in our classification, the complete classification construction we gave, which is expressed in terms of certain ramification properties and maps to the moduli space of K3s, of MN polarized K3s, precisely coincides with the description of the degeneration geometry and the blowing up that you have to do to make them quasi-Fano on the mirror side. So it's a very, very precise, and again, we sort of developed these two things. I know the names are the same, right? But we developed these two projects in parallel. We weren't necessarily looking to make this connection when we first started doing the classification, but it provided wonderful evidence, and I should say evidence beyond the toric regime. You're not limited to not beyond the toric regime, beyond the hypergeometric regime. You're not limited to M1 through M4, the families of K3s with hypergeometric variation. Okay, so of course you want to go back to the other mirror constructions and check compatibility. So if you go back to the Batchery-Borzov style mirror construction for torically induced fibrations, that is fibrations that come from fibrations on an ambient toric variety and restrict to hypersurfaces or complete intersections, that works. And this was also studied in the balanced case, I would call it, with fibrations and degenerations on both sides by Lee. The reduction in the case of abelian varieties, so starting with elliptic curves and then up to higher dimensional abelian varieties, the reduction to the Strominger-Yau-Zaslow mirror construction is something that Tsushi Kanazawa worked out back when he was a postdoc with Yau. Compatibility with homological mirror symmetry conjecture under the Turin generation is something that Harder and Katsukov investigated and confirmed. It implies a notion of lattice polarization on both rational elliptic surfaces and Del Pezzo surfaces coming from that of K3s. So if you think about the K3 case, what we're saying is that a K3 surface on the one hand is degenerating to a pair of weak Del Pezzo surfaces intersecting on an elliptic curve. And on the other side, you have your two Lambda Ginsburg models, but the Lambda Ginsburg models are effectively rational elliptic surfaces with a fiber at infinity missing, right? So, and those are supposed to glue to give a lattice polarized K3, which is the mirror to the first. Well, the K3s have these beautiful lattices, the K3 lattice, and you can check what the induced lattice structure is on the various pieces and how they glue together. In a very refined sense, this is something that Alan Thompson is working on with his postdoc right now in Loughborough, and some wonderful results are coming out of that, and it ties into KSBA compactifications, and it's a marvelous story. Okay. The DHT construction also leads to what we call a B-model derivation of absolute to relative degeneration formulas for genus Serogrom of Witten invariants under a Turin degeneration. So what does all this mean? A motivation for mirror symmetry interest in mathematics has always been the predictions of Candelas, Delosa, Green, and Parks involving enumerative predictions of mirror symmetry, curve counts, counting rational curves of various degrees, and things like that. The theory of Gromov-Witten invariance was developed to address this kind of question. An early problem that was addressed in Gromov-Witten theory, it goes back at least to Jun Lee, is when you have a family of manifolds on which you're applying your Gromov-Witten methods for enumerative geometry, and you degenerate, like for instance, the Tyurin degeneration of a Calabi-Yau threefold, what happens to those curves? What happens to those curve counts? Can you reproduce the curve counts from counts on the pieces? And there are various degeneration formulas due to Jun Lee, and I think Poddar and Malik might have one, various ones. We, working with my former student, Jordan Kostiuk, and Fenglong, who's an expert on relative Gromov-Witten invariance, we were able to show that, in fact, there is a formula, okay, for such invariance in the enumerative side that is merely a direct application of a very simple operation on the B model side, so on the gluing side. So, in effect, by gluing periods on the Lambda Ginsburg side, the fibration side, we're able to combine that with relative mirror maps in such a way, mirror maps and relative mirror maps in such a way to give a B model derivation of such a degeneration formula. Now, it's quite a different matter to match what we do with what's already been proved in the literature, and that hasn't been done yet. But what we have is the proof. It's absolutely true, and it's matching the behavior of the fibration side. Okay. This also connects with the Gross-Seibert program through log deformation theory and tropical geometry. This is an ongoing project with Lawrence Barrott, and it's also something that we're working on with Fenglong Yu. And the reason for that is because, again, one would like to tie the DHT mirror, at least in some cases, to another form of mirror symmetry that's already been proved. Okay, so Kanazawa related it to SYZ, and at least in low-dimensional cases that he was looking at, SYZ followed. Well, he was looking at low-dimensional cases, then also abelian varieties, and so there, SYZ was a known result. The algebro-geometric analog of Schrödinger-Gauss-Aslam mirror symmetry is the full Gross-Seibert program. And what we were able to do under certain hypotheses is show that you can reduce some of the predictions of DHT to what you get from Gross-Seibert. That's very much work in progress. We're not there yet, and we certainly can't say that we have like a Gross-Seibert theoretic proof of DHT in any real, full generality. But we're chipping away at all the problems along the way. And then one of the difficulties that shows up is if you want to get inspiration from the work with Kostiuk and you have to relate, or you'd like to relate directly, if you could, the relative Gromov-Witten invariance that Tseng and Yu have developed with the pointed Gromov-Witten invariance that show up in Gross-Seibert. And that's another big open question. So there's a lot going on there. And finally, it suggests a mirror version for fibrations of the Clemens-Schmid four-term long exact sequence associated to a degeneration, and a perverse refinement of the Hodge diamonds on both sides. And in the time that remains, which is about 20 minutes, I want to focus really on this particular application. So this is something that I did with Alan Thompson, working on it for many years, and it really is a nice case of something which is a provable theorem. The mirror of the Clemens-Schmid sequence. We prove a sequence, a four-term exact sequence, long exact sequence, which we claim. We prove it as a theorem, and we claim that because of DHT, it should be thought of as being mirror to the Clemens-Schmid sequence. And then we do a bunch of examples and see implications and do some conjecture. So let me switch to that now. If I've done this right, I can just click a couple times and I'm there. There we go. Okay, mirror Clemens-Schmid sequence. I'll change the orientation. There we go. So what I want to do here is I'm talking about this archive paper with Alan, okay, from last year. I'll start by zipping through some background on perverse Larray and the original Clemens-Schmid sequence. And then I'm going to focus on the statement of the mirror theorem and the statement of an associated conjecture and say something about examples. I might skip the K3 and just jump to the Calabi-Yau threefold, depending upon time. Okay, so the idea behind the perverse Larray filtration is that lots of data about a fibration, pi from Y to B, is encoded in the Larray spectral sequence. Okay, it abuts the Larray filtration, but it happens at E infinity. Okay, and you really prefer it to not have that. You know, I think I can go the other orientation. I think it fits. I think I did the talk that way. There we go. So it abuts the Larray filtration, but this is an E infinity convergence, which is kind of annoying. You really like something to converge maybe at E2. So the problem is that the Larray spectral sequence only degenerates at E2 under very special circumstances. So for example, if pi is smooth, well, that's ridiculously strong. Or the base is one-dimensional. Well, maybe that's enough for you, but it won't be for us in general. So the solution is to consider instead the perverse Larray spectral sequence, okay? And in 2010, Di Cataldo and Migliorini gave a geometric interpretation for the perverse Larray filtration. It computes the same thing, but it has some very nice properties. In particular, the perverse Larray filtration degenerates at E2 under very weak assumptions. For example, when pi is projective, which is great. It's going to be true for pretty much any example we're interested in. Okay, so what about the Clemens-Schmid sequence? What is that? Well, if you let X over a disk be any semi-stable degeneration, so what do I mean by that? Well, okay, the degeneration is going to be a proper flat surjective morphism from a Kähler manifold of dimension n with connected fibers smooth over the punctured disk. Okay, it'll be semi-stable if the central fiber, the fiber over the puncture in the disk, has the property that inside the total space, script X, it's a simple normal crossings divisor. Okay. And there's various theorems about the existence of and algorithmic approaches to semi-stabilization for degenerations. But let's just make this the simplifying assumption at the moment. Then if you let xt denote the generic fiber, so basically T non-zero, okay, then the Clemens-Schmid sequence is the 4-term exact sequence of mixed Hodge structures defined as follows. You've got the inclusion of your x naught into your x, and the first term is hk of x, and this is a perverse shift. Then you have the limiting mixed Hodge structure, hk of the fiber, xt. Then you have the log of monodromy map to hk lim xt, but with a Tate twist. And you have I upper star here, and you have I lower shriek here, okay? So how do the mixed Hodge structures work? Well, in this case, it's just, you know, by retraction, you can reduce this to being isomorphic to hk of the fiber x naught. And then Deligne gives a mixed Hodge structure in any normal crossings variety. Remember, we assumed it was normal crossings. You build it up that way. So that's how that works. For this one, you get to use the usual cohomology of xt with its limiting mixed Hodge structure. And that's also defined in a way that involves chopping things up, but I won't go into details on that. This one here is Poincare dual to h2m minus k of x, and that gets a mixed Hodge structure from Hom, h2m minus k upper x to q. So everything gets a mixed Hodge structure on it, and you have to tune, as I said, the degrees for, you have to do a little Tate twisting for that, and you have to tune the degrees to the perversity. What you find is that terms in the Clemens-Schmid sequence admit 3 filtrations. There's the Hodge filtration, the weight filtration, and the perverse Larray filtration. Okay. And if you have a fibration over a disk such that the weight filtration and the Hodge filtration define a mixed Hodge structure, they do it on a mixed Hodge structure on not just the whole cohomology, but actually on the graded pieces of the perverse Larray filtration. So this is a definite refinement of your usual kind of HPQ picture, right? All right, so this is the theorem. I'm quoting Kurlaza from last year just because it's a convenient reference point. neither we nor they claim that they're the originators of this particular result. This is just, they put it all in one place. It's very nice. There's also a very nice appendix to their paper by Saito. So it's it has some new results in it, but it's a really good reference. And the Clemens-Schmid sequence is exact for all three of these filtrations, and is an exact sequence of mixed Hodge structures on the graded pieces of the perverse Larray filtration. Okay, so that's a summary, if you like, of the story for Clemens-Schmid, the really good story attached to degenerations. Okay, but if we want to mirror Clemens-Schmid, well, we need a philosophy that tells us what the mirror of a degeneration is. And I already told you that the DHT philosophy is that degeneration is mirrored to fibrations. Okay, this is just a quick recap of what I said before. You can imagine taking a Calabi-Yau n-fold and degenerating it into a pair of quasi-Fanos intersecting on a Calabi-Yau n-1 fold, the so-called Tyurin degeneration. Andrei Tyurin, actually, in one of his very last lectures, perhaps his last lecture and posthumous paper, said going backwards in terms of smoothing that this might be a great way to construct lots and lots of Calabi-Yau manifolds. He didn't go so far as to claim that they could all be constructed in this way, but he certainly indicated that this was a great way to construct them, sort of undegeneration, however you want to call it. In any case, assume you have a Tyurin degeneration here on this side, and what we said is that you take the mirror of each of these two quasi-Fanos and you get a pair of Lambda Ginsburg models. They're fibered by the mirror of this guy, and then you glue them and you get a fibration of the mirror of this over P1 fibered by the mirror of this. Okay, and then this is the things we mentioned before already. All right, so the goal then, now that we accept the DHT philosophy as a motivation, is to find a mirror to the Clemens-Schmid sequence, and it had better involve fibrations. So here's our setup. We let Y be a smooth projected complex variety. We let B be a smooth projected complex variety with a fixed embedding into projective space. We let pi from Y to B be a projective surjective morphism. Now you might say, wait a minute, that's much weaker than a fibration. And the answer is yes. And that's great, because this means it also works for birational maps, birational contractions, and it works for non-flat maps that are finite to one, all sorts of great stuff, okay? So you get a whole bunch of sort of generalized fibrations that satisfy these very weak conditions, and our result's gonna apply. Also notice, I didn't mention Calabi-Yau anywhere on this page, because the result won't depend on it. Clemens-Schmid didn't depend on Calabi-Yau, right? All right, so let's let C and B be a general linear subspace, just an intersection of our base B with the general hyperplane in PM, because remember, it's embedded there. Think of it like a very ample embedding. Okay, so now what is Z? Well, I'm going to let Z be pi inverse of C in Y. Okay, so for example, if B is P1, C could be a point, and then this could be a fiber, right? Think of it that way. U is the complement of Z in Y. So if you want to think of it as the complement to the fiber in the total space of the vibration. And we're going to let M denote the dimension of B. It'll come up later. Okay. So if you actually ask what the description of Di Cataldo and Migliorini of the perverse Larray filtrants are, you see that you actually get that the ELF would be the kernel here, where it's the kernel of the map from HKUQ to HKUQ restricted to U intersect one of these pieces, Y sub K minus L minus 1. So I have to tell you what Y sub K minus L minus 1 is, and it's beautifully defined. And the geometry is so elegant here. Y naught is just Y, fine. Y minus 1, and the way it's set up, you have minus indices, is pi inverse of C prime, where C prime is linearly equivalent to C, fine. Y minus 2 is pi inverse of C prime intersects C double prime, where both C prime and C double prime are linearly equivalent to C, etc. You just keep doing this more and more and more. And finally, Y minus M minus 1 is the empty set. Okay, so this is enough information geometrically to reproduce this. And you get a similar description for the other terms you care about. HK convexly supported U and HK of Y. So This is easy. This is a little more work. So a proposition from the paper with Thompson, which is essentially from Di Cataldo Migliorini 05. They don't state it exactly, but it doesn't take much work. We don't use anything beyond their paper to prove it. Is that up to a shift, the perverse Larray filtration on H star of Y agrees with the weight filtration of the nilpotent endomorphism. Okay, now we had such an endomorphism on the other side of the Clemens-Schmid sequence, and it came from nu. It was the monodromy weight filtration, and nu was the log of monodromy operator. Now it's a filtration of nilpotent endomorphism that you get by cupping with the class of Z. That's it. Okay, that's the basic connection. And using this and some more or less standard technology that parallels the Clemens-Schmid long exact sequence proof, we show with Thompson that there is a 4-term long exact sequence, HK complexly supported U, HKY, HK plus 1Y, so the Tate twist, K plus 2Y, HK plus 2U, the Tate twist. And this map is given by cupping with the class of Z. And the theorem is that this is exact for all 3 filtrations, and is an exact sequence of mixed Hodge structures in the graded pieces of the perverse Larray. Okay, so I'll just note that the proof uses an interlacing of localization along exact sequences. You sort of have a long exact sequence here, you have a long exact sequence here. This one goes something involving U, Y, Z, U, Y, Z, U, Y, etc. This is U, Z, Y, U, Z, Y, something, etc. With these various indices. And then this part, with this dashed map, that becomes the basic 4-term sequence for Clemens-Schmid. So it's a beautiful story. This is a theorem. This has nothing a priori to do with mirror symmetry. We call it the mirror Clemens-Schmid sequence because of our motivation, and we'll see why in more detail. But it's not actually depending on mirror symmetry. It's not depending on Calabi-Yau manifolds or anything of the sort. Okay, so once you have something like this, you can't resist computing. And explicit computation of examples of families of Calabi-Yau varieties led us to what we call a mirror P equal W conjecture. Okay, so if X and Y is a mirror pair of Calabi-Yau n-folds, now for our conjecture, we don't care what construction you use. We're saying, hey, no matter what construction you use, this should be true. Suppose further that X undergoes a semi-stable degeneration with nilpotent log monodromy operator nu of index M. Okay, so it's sometimes known as a type M degeneration. Then 3 things should be true. First of all, Y, the mirror to X, should be fibered over a base B of dimension M minus 1. Okay, so the index here, minus 1, should be the dimension of the base. And secondly, the dimension of, okay, now I'm going to do graded pieces, but this is slicing and dicing the graded pieces because we have F, W, and P type filtrations to work with, right? So, monodromy weight filtration, perverse Larray, or weight filtration, perverse Larray, and Hodge. The mth, qth, elf of HKY, we claim, can then be identified with the n minus mth, n plus L minus 2mth, n plus Q minus 2mth of the limiting mixed Hodge structure on XT degree n plus K minus 2m. And this is, again, just work out some examples, enough examples, and you see the pattern. And finally, also, that dimension of the mth, qth, elf of the compactly supported cohomology on U is the dimension of the n minus mth, n plus L minus 2mth, n plus Q minus 2m plus 1 of H n plus K minus 2m of the total space of the degeneration. All right, so quick remark. This seems to be a Calabi-Yau version of the mirror P equal W conjecture for Fano LG models of Katsarkov, Truskowski, and Harder from 2020, okay? And after the fact, we checked that if you believe DHT, then there is a direct link between the two. I mean, it seems, and we'll have to work out some details, that our conjecture here, you then apply DHT, would imply theirs. Okay, or alternatively, you prove theirs and work out these necessary steps in terms of smoothing, and it could imply these formulas for Calabi-Yaus. I have 5 minutes left, is that right?
Yes, 5 minutes.
Okay, perfect. So I'm going to skip the K3 surface examples, like I said, where we check these things. And I'm just going to focus on now the example of the quintic threefold. Okay. So if you have quintic threefolds, what are the natural degenerations? Well, it's a quintic hypersurface. So 5 can be written as 1 plus 4 or 2 plus 3. Okay. And if you write 5 as 1 plus 4, your degeneration is into a hyperplane. So a threefold hypersurface of degree 1 and a quartic threefold. If instead you do 5 as 2 plus 3, you get a quadric and a cubic. Okay. Now, I have to say, you actually, to get a Tyurin generation, this has to be smoothable to this. This has to be smoothable to this. And for that, you have to do more. You have to do some blowing up. So you have to blow up, for instance, in here on a degree 20 curve on V1, for example, right? There's some blowing up that you have to do to make this happen. But anyway, the point is that when you do the suitable blowing up, so resolve, you see that this Tyurin degeneration here is a hyperplane uniquartic glued along a K3 surface of degree 4. And of course, 4 is 4 times 1. Okay. You do the same thing here. Your quadric and your cubic are glued along a K3 surface of degree 2 times 3 is 6. And then of course, you have to have the resolution. And you can do a further degeneration of both of these down to, well, 2 hyperplanes and a cubic hypersurface, and do the resolution. I didn't say K3 because there's no more K3. Actually, you end up getting a common intersection, which is an elliptic curve that you have to work with, which is wonderful because that fits into our picture and says that we should have an elliptic fibered Calabi-Yau threefold over a surface mirror to this. We should have K3 surface fibered Calabi-Yaus mirror to each of these. Okay. And you can do it. You can compute the filtrations. If you do the GER2F, GER-W3, GER-F3 of H3 limb, it works out to H21 of V1 plus H21 of V4. This one's rigid, so nothing. This one actually has 30 plus the genus of a particular singular curve, which is 51, and it adds to 81. You then do the mirror quintic. Now, by a result in that big classification we did, the very useful big classification of MN polarized K3 fiber Calabi threefolds, Y admits fibrations by both K3 surfaces of, this is mirror to, the K3 surface mirror to degree 4 and 6. So M2 and M3 is what I mean to say there. And if you have a point in the base P1, right, and you consider Z to be the fiber, the corresponding K3 fiber, you can run the same game, and you get, by calculations done in another of those papers of ours, that this is the sum over the fibers of the number of components minus 1, which turns out to be 30 plus 51 is 81. Okay. I should point out the conjecture I stated didn't say this had to match this and this had to match this. So there's clearly room for refinement already, what we're saying. And then if you do the third case, building on work in the second paper with Kostiuk and Yu, you can actually work out in detail the elliptic fibration on Y, which is mirror to the depth 2 generation, if you like. And it's compatible with both M2 and M3 polarized K3 surface fibrations. So in other words, Y is elliptically fibered over a surface B. B admits projections, maps down to 2 P1s, and the composition is fibered by a K3 of M2 type there and a K3 of M3 type there. Okay, and then you compute the filtrations for all of these, and they match. So I'll finish there, right on time.
Well, thank you very much for a very interesting talk. Are there any questions? Okay, I have a couple of questions. So the first one is, when you are looking at mirrors of vibrations, And you said they're not fibrations, but they are built out of these two pieces like Quasi-Fono glued along Calabi-Yau. So how did you come up with this? What is the idea behind? I mean, how did you guess that this could be like this? And
yeah, so that's a great question. What happened in the very early days was a lot of just example checking, right? So we knew of a particular subclass, which I used to call balanced toric fibrations, where mirror symmetry a la Batira-Borisov had the property that it respected the fibration structure. In other words, that the mirror, say, of a Calabi-Yau threefold that was K3 fibered would be fibered by the mirror K3s. But I also knew that it was incredibly special, right? And so what we were trying to do is we were trying to understand this complete class of Hodge theoretically motivated MN polarized K3 fiber Calabi-Yau threefolds. And that moved us beyond the toric world. And as soon as we got beyond the toric world, we began to see the kind of patterns, we're talking about here. And we began to realize, I mean, I had learned through computation with my student, Andrei Nicolaevich Tyurin, many years ago, back when I was working on the first paper with Morgan, that there were K3 fibrations on the quintic mirror. And those were torically induced, in fact. So I knew about those. And we started asking these questions about regularity of the K3 fibrations in the list of 14. And so I think we were doing a lot of things around the same topic. And then gradually the haze, I mean, I'm in Berkeley right now, and every morning I look out and I see the fog over San Francisco, and sometimes that fog lifts and you can see downtown. That's what eventually happened. Yeah. And then, questions like, gee, if we believe that our philosophy is fibrations or mirror degenerations, then anything and everything about the generations ought to have a mirror story involving fibrations. And that's what led us to look very carefully at the Clemens-Schmid sequence. What was very satisfying was that we didn't have to work too hard in the end. I mean, we were trying to build it all by hand. Like, we went into the proof of Clemens-Schmid, and Alan and I were looking at the individual threads, and we were trying to build it all by hand. And then eventually we realized that the missing ingredient was perverse Larray. And then it just made it all click into place beautifully.
Okay, thank you. I have one more question. Like, maybe you mentioned something, but I couldn't fully, maybe you mentioned very briefly. So this, towers, do they help in constructing SYZ mirrors, or is there any connection to the SYZ?
Yeah,
story?
that's a good question. So there's a direct connection to SYZ that you can make in low dimension. So if you're talking about Calabi-Yaus of dimension 1 or 2, for 1, it's easy, and Kanazawa made that connection complete, very early on in one of his papers on the subject. For the next dimension up, where we're talking about elliptically fibered K3 surfaces, it's clearly related, but it's related through such things as having to rotate the complex structure to get a Lagrangian fibration. It plugs into an old story of Gross and Wilson, for example. So there's something to say there, but I don't think it's particularly interesting in those dimensions. Where it gets really interesting is, say, for Calabi-Yau threefolds. And this ties in a little more to what I'm trying to do with Lawrence Barrott and Fenglong, in the sense that there, the right thing to do is to use the Gross-Siebert analog of SYZ. And when you do that, you are led to very interesting questions about tropical geometry and variance on unobstructedness theorems. And there's still some work to be done. But what one expects is there to be a sort of robust connection there. There's some subtleties, right? One subtlety is it's not clear that whether you should assume that you're connected in moduli to maximal degeneracy. And the SYZ picture, from its inception, was always motivated by the fact that you're coming from a maximal degeneracy perspective, right? I remember when Eric Zaslow was first working out those calculations for that paper, that was his motivation. And he was, I got the impression he was frustrated that you had to work in the degenerate limit, but that's the reality. The SYZ proposal just doesn't work unless you take into account that degeneracy. Everything I'm talking about here doesn't require it. It works for any kind of modest degeneration. The formulas still work. And I think I might have mentioned this on Tuesday, but what I find remarkable also is that there are hints of this in the original Candelas-Delosa and Parks paper. When I workshopped that with my students, I realized that one of their arguments to compute the periods associated to one of their integral cycles really reduced to working with a 3F2 that then became, after a complicated argument, a 4F3. And so that's exactly what was happening. They were actually computing the fiber-wise periods on quartic mirror K3s and using those in a miraculous formula kind of way to get the periods for the quintic itself. So quintic mirror itself. So so I think a lot of strands are sort of coming together now, and we have a very robust approach to the toric setting now that we're working out with Fenglong and David Fivero, that makes all of the gluing formulas for periods seem very natural in a toric setting, So I'm confident there's a lot to do with this story, and I'm extremely interested in pursuing with collaborators the arithmetic applications. It's something I've mentioned to Barry Mazur, and I'd love to talk to Ling about it. Maybe we'll talk in January about it, Ling, or before. I think because this is a form of mirror symmetry that is compatible with the traditional one, but doesn't have the sort of extreme geometry, extreme degeneration associated with that, or doesn't rely upon something like an SYZ fibration. I think it plays well and will play well with arithmetic considerations.
Thank you. That's very insightful. So, are there more questions from the audience? Okay. Yeah, Devendra?
Perhaps not, yeah. No questions.
Okay. So let's thank Professor again. And so thank you very much. And
thanks, Professor Poddar, also for chairing this talk. And thanks, Chuck, for the wonderful course on Calabi-Yau threefold.
Okay, thank you very much. And and hi, Ursula.
yeah, we will see.
Hi. Hi, Chuck.
Hey. Where are you now, Ursula?
I am back in Ann Arbor.
Okay. Great. Well, we should chat soon.